Hello, this is Adib Mohammed Tausif, an undergraduate student from the Department of EEE BUET. So today I'm here to talk about P-N junction diode device physics and applications. So before diving into what a P-N junction diode is, we will know about what is actually a P-N junction. A P-N junction is a boundary or interface between a P-type and an N-type semiconductor. What results in a P-N junction is that due to the diffusion of the majority carriers from P side and N side, we can say that a depletion region or a space charge region is created. So in the figure, this is called the space charge region, which is mainly the result of majority carrier diffusions from P and N types, respectively, leaving charged ions. There exists an electric field in the space charge region which directs from the N side to the P side. So this space charge region is basically responsible for the directional property of a P-N junction. Now, what is a P-N junction diode? So a P-N junction diode is a semiconductor device that allows the flow of current in one particular direction only. So how does this actually happen? So before knowing this, we will know about what is meant by biasing an electronic component. So biasing is actually the process of applying external voltage to the semiconductor device. Particularly for P-N junction diode, there are two types of biasing. This is called a forward bias and reverse bias. So what is actually forward bias? Forward bias means that if we connect the positive terminal of the battery to the P side and the negative terminal of the battery to the N side, this results in a forward bias, and the opposite results in reverse bias, which is actually the positive terminal to the N side and the negative terminal to the P side. So this is how actually a P-N junction diode is biased. So observing the biasing schemes, we can say that in reverse bias, the depletion width or the width of the space charge region increases, and in the forward bias, the width of the space charge region decreases. As in the previous slide, we can see that there is an electric field present in the depletion region, which is actually responsible for hindering the flow of current. So we can say that due to the increase of depletion width, in reverse bias, there is actually very negligible or no flow of current, while the forward bias facilitates the flow of current by shrinking the depletion. So this is actually the characteristic of the P-N junction diode. So a P-N junction diode presents an exponential relationship between the current and the voltage. Now, if we bias a diode with a variable DC source, and if we change the voltage, we will be observing the following relationship between the voltage and the current of the P-N junction. So where here IS is the reverse saturation current, which is dependent on the dimensions and the doping profiles of the particular P-N junction diode, and which is Vt is the thermal voltage given by KT by Q, where K is the Boltzmann constant, T is the temperature in Kelvin, and Q is the electronic charge. And N is actually the ideality factor, which is taken as one for most common cases. So observing the P-N junction diode characteristics, we can see that after a particular voltage, the current increases very much sharply. So this voltage is actually called the cutoff voltage. For a very common silicon diodes, the cutoff voltage is actually 0.7. So if we mention that our diode is ideal, the cutoff voltage is actually 0. That is, any voltage greater than 0 would make the diode turned on. That is, it will conduct electricity. So this is the forward bias region, and this is the reverse bias region. In the reverse bias region, we can see that there is a very negligible amount of flow of current, and after a particular voltage, which is known as the breakdown voltage, the current increases abruptly. So this huge increment of current is due to the device being malfunctioned, which is also known as breakdown. So if we summarize what we learned in this slide, is that there is an exponential relationship between the current and voltage of the P-N junction diode, making it as a nonlinear device. It is basically a very primary nonlinear device we'll be studying in the electronics. And nonlinearity actually means that there is no linear relationship between the voltage and the current, which we have seen in the Ohm's law for a resistor. So now we will be seeing the applications of a P-N junction diode. So P-N junction diodes are used to make rectifier circuits. What is a rectifier circuit? Is that a rectifier circuit converts an alternating current signal to a direct current signal. So an alternating current signal is that it changes polarity with time. Whereas a direct current signal means that the polarity is always fixed. That is only positive or only negative. So this is a DC and this is an AC. So a rectifier is actually a key component for making the DC power supply, and the directional properties of a P-N junction basically helps us to make a rectifier circuit. So this is actually a DC power supply block where we can see that there is a diode rectifier, which we'll be seeing in the upcoming slides. Now we will be talking about a half-wave rectifier. What is actually mean by half-wave rectifier is that the half-wave rectifier only rectifies or converts, only rectifies the half wave of a sine wave. What is meant by this? We will be seeing in the following circuit. If this is actually the Vs, which one is marked by me. If we apply the Vs in the first half cycle or the positive half cycle, the diode there is a possibility of the diode being forward biased after a particular cutoff voltage. Here, it is a practical diode is considered. So after a particular cutoff voltage, the diode will get forward biased and it will be conducting. So the current will be flowing this way, and we will eventually get a voltage like this. Now, in reverse bias, the diode will be non-conducting, and there will be no current in the circuit, resulting in a zero voltage. So this is actually the functionality of a half-wave rectifier. If we see the transfer characteristics, that is the relationship between the output and input, we can say that after the particular cutoff voltage, the voltage increases with current with a slope of 1. Now we will be seeing a full wave rectifier. A full wave rectifier functionality is basically same as the half wave rectifier. The only difference is that here the both of the half cycles of the sine wave would get rectified. So this is a center tape rectifier and this is a bridge rectifier. So the center tape rectifier is basically the same as two half-wave rectifiers connected in proper connections. So we can see that during the positive half cycle, this diode gets turned on, resulting in output polarity of this across the resistor. And in the negative half cycle, this diode gets turned on and this diode gets turned on and this diode gets off, and the output polarity is actually the same in the resistor. So we can say that for both the half cycles, for this one and this one, we are getting the output as this one. And now this is actually a bridge rectifier. In a bridge rectifier, in the forward half cycle, this diode and this diode conducts, resulting a polarity of this. And in the reverse bias, these diodes and these diodes, in the negative half cycle, this diode and D3 and D4 conducts, resulting a voltage polarity of like this. So we can say that for both the half cycles, we are getting the same polarity of the output voltage. So in this way, we can achieve the full wave rectification using bridge rectifier circuits and center tape circuits. Now we will be talking about clipper circuits. So clipper circuits are network that employs diodes to clip away a portion of the input signal without distorting the remaining part of the applied waveform. So this is actually a clipper circuit. In a clipper circuit, we can see that there is a DC 5-volt biasing. And when the input is less than minus 5 volt, then we will get no output. When the input is greater than minus 5 volt, we will see that there is an output. The output is actually here Vi plus 5. Applies that Vi is greater than equal to minus 5. And output is equal to 0 when Vi is less than minus 5. So this is actually a clipper circuit. Now a clipper circuit actually shifts the DC level of a circuit. It is important to note that a clipper circuit must have a capacitor connected with the input. So this is the figure of a clipper circuit. Now the functionality of the clipper circuit is basically the capacitor resistor, basically dependent on the capacitor resistor transients. So in the positive half cycle, or from 0 to T by 2, the capacitor gets charged to C, shorting the output to 0. So we can see that. And in the reverse, in the negative half cycle, we can see that the capacitor retains its charge of V, and applying a simple Kirchhoff's voltage law, we will be seeing that the output voltage across the capacitor is minus 2V. So we can say that the output swing for both the input is and output is equals to 2V. Here is also 2V. Here we also can see that the output swing is 2V. The DC level is just shifted. Now we will be talking about Zener diode. A Zener diode is a semiconductor diode which is designed to operate in the reverse breakdown region. So in the forward region, it is actually same as a simple P-N junction diode. But in the reverse region, we can say that after a particular reverse breakdown voltage, the voltage remains fixed at Vz despite variations in the input voltage or load conditions. So this property of a Zener diode is called voltage regulation. So if we have a voltage source like this, and if we have a Zener diode like this, this is a symbol of the Zener diode. If the voltage is greater than or equal to Vz, or the breakdown voltage, then the V output, this is the V output, the V output will be fixed to Vz. So this is the functionality of a Zener diode is a voltage regulator, which has ample applications in the electronics world. Thank you very much. This is all about P-N junction diodes.